So far, we have been approximating areas using rectangles, which is great because the area formula, base times height, is so super easy to use. But we've seen that curves don't really play so nicely with rectangles, right? We've got these triangles that are too big, or these triangles that are too small, and we have a whole lot of error in our estimations, whether this might be an RRAM situation for this diagram or an LRAM situation like in that one. And we tried to split the difference here with the MRAM, and that might be a little bit better, but all of them leave a lot to be desired because of these inaccurate rectangles. So we're going to try to think outside the box a little bit, and instead of drawing horizontal tops to these little areas, we're going to draw diagonal lines connecting one endpoint to another. So what we're getting at here is that we would not say, for example, take this to be the top of a rectangle and then just extend it out over here, because that would make it too big. But we would not take this one and say this is the top of the rectangle and say, oh, that's too small. But instead, we'll connect them diagonally, to connect these 2 points on the curve diagonally with a little secant segment. And that's going to be a better approximation of the area under the curve. Of course, it's still not exact because our curve is a curve and not a series of straight lines. But we can kind of use that directional idea to get a much more accurate estimation. So this is actually creating trapezoids. Remember that a trapezoid is a quadrilateral with two sides that are parallel. And we need to figure out what the area formula of the triangle is. Now, there are a number of ways you can figure this out. You can break it into a triangle and a rectangle. If that's what you prefer to do, that's fine. Or you could do that little thing in geometry where you take that little piece and you switch it over to here and you get a rectangle instead. Whichever way you want to think about it, I don't really care. Just know that the formula works out to be the area of a trapezoid if the bases are y1 and y2. We're going to average y1 and y2, y1 plus y2 divided by 2, and we're going to multiply that by the height. The height is sideways here, but it's our delta x. Whoops. So it's generally nicer to factor out that 1/2 and have y1 plus y2 and then times delta x. And that's going to give us the area of your generic trapezoid. So we'll give this thing a try in a minute, but first let's learn this new notation. This should look a little bit familiar to you, but we now have numbers here and here. It looks like we're talking about an antiderivative, and it turns out there is a relationship between antiderivatives and the area under the curve. But for now, let's just accept that this definite integral from a to b of the function f of x dx is going to represent the exact area under the curve between x equals a and x equals b. So that's the notation we're going to see a lot in this section. So when I say approximate the definite integral from 0 to 8 of x squared dx, here's my curve, y equals x squared. We're starting at an x value of 0, we're ending at an x value of 8, so those are our horizontal bounds of our pink area, and it's the area under the curve. So this picture represents the area that we're looking for, and this definite integral also represents that same value. So we're going to go ahead and try to find the area using the trapezoidal method if n equals 4. So what that means is we're going from 0 to 8, and we know that we're going to divide that up into 4 equal subintervals. So our first subinterval is going to go from 0 to 2. Our second subinterval is going to go from 2 to 4, 4 to 6, and 6 to 8. Those are 4 equal subintervals from 0 to 8. So that's going to be our delta x value, right? So delta x, as always, is equal to b minus a over n. In this case, b is 8, and a is 0, and n is 4. So that's our value 2. Delta x equals 2. And that's going to be true for each and every one of those trapezoids. So the heights of the trapezoids are going to be determined, just like with the rectangles, they're going to be determined using the function f of x equals x squared in this case. So what we need to do is find the left height and the right height of the first trapezoid, f of 0 and f of 2. And then we're going to find the left height and the right height of the second trapezoid, the f of 2 and f of 4, etc. And you're going to notice that the f of 2 and the f of 4 and the f of 6 get used twice, whereas the f of 0 and the f of 8 end up only getting used once. So we can actually combine this all together and say, well, let's see. The integral from 0 to 8 of x squared dx is going to be approximately equal to, let's see, our delta x value is the same for all of those, so that's going to be 2. Well, let's put that at the end, actually. I prefer that at the end. We have the area formula is 1/2 times the sum of the two heights, and then times dx. And then it's going to be f of 0 plus f of 2, and then f of 2 plus f of 4, and then f of 4 plus f of 6. So because we're using f of 2 twice, I'm going to do 2 f of 2. And because we're using f of 4 twice, I'm going to go ahead and say 2 f of 4 and 2 f of 6. Notice that we only have one f of 0, we only have one f of 8, because those are heights that don't get used twice. Okay? So this one works out pretty nicely because the 1/2 and the 2 cancel each other out. So we've got f of 0 is 0 plus 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6 plus only 1 f of 8. And then we can add these up, which I believe is 176. So again, this would be the approximation of the area under the curve using the trapezoidal method and 4 equally spaced trapezoids.